Imagine a star racing through space at 3% the speed of light, so fast, it could circle Earth 100 times in a single second. This isn't some distant cosmic oddity, it's hurtling around the supermassive black hole at the heart of our galaxy, Sagittarius A*, in a deadly dance of gravity and light. At just 120 times the Sun's mass, the black hole's pull is so intense that this star, named S2, orbits it in a mere 16 years, yet it survives, defying the crushing tides of spacetime. Scientists have watched the star's journey for decades, using telescopes to trace its path as it schemes within 100 times the Earth-Sun distance from the event horizon. What secrets does this extreme environment hold? How does such a star resist being torn apart? And why does its orbit reveal the black hole's hidden mass? This is the story of a cosmic tightrope walker, balancing on the edge of oblivion, and the universe's most powerful gravitational force. Astronomers have discovered a star hurtling through space at incredible speeds, orbiting the supermassive black hole at the center of our galaxy. This star, moving at velocities far exceeding those of most other stars in our Milky Way, provides a rare glimpse into the extreme gravitational forces exerted by Sagittarius A*, the black hole that anchors our galaxy's core. While stars orbiting black holes are not unheard of, this particular star's speed and trajectory have sparked new questions about the dynamics of stellar motion in such extreme environments. The discovery offers a unique opportunity to test the predictions of Einstein's general relativity and deepen our understanding of how supermassive black holes shape their surroundings. Let's explore what this star's journey reveals about the cosmos and the forces that govern it. To grasp the significance of this star's motion, we first need to understand the environment it inhabits. At the heart of the Milky Way lies Sagittarius A*, a black hole with a mass over 4 million times that of our Sun. Despite its immense size, this black hole is relatively quiet compared to some of its counterparts in other galaxies. Its gravitational pull is so strong that it warps the fabric of spacetime around it, creating a region where the rules of classical physics break down and Einstein's theories take center stage. Stars in the vicinity of Sagittarius A* orbit the black hole at high speeds, but most of these stars follow paths that are only slightly faster than those of stars in other parts of the galaxy. This particular star, however, is moving at a velocity so extreme that it stands out as an anomaly, a cosmic outlier that challenges our current models of stellar dynamics. The star's speed is not just a matter of distance covered over time, it's a direct result of its proximity to Sagittarius A*. The closer a star is to a black hole, the stronger the gravitational pull it experiences, and the faster it must move to remain in orbit. This star, however, is not just close, it's in a region where the black hole's gravity is particularly intense. Its orbital period, the time it takes to complete one full revolution around the black hole, is shorter than that of most other stars in the galactic center. While astronomers have long studied stars orbiting Sagittarius A*, this star's extreme velocity suggests it may be part of a rare class of objects that have been influenced by the black hole's gravitational forces in ways not yet fully understood. This could mean that its path is shaped by factors beyond simple gravity, such as interactions with other stars or the presence of dark matter in the galactic core. The discovery of this star was made possible by advanced observational techniques that allow astronomers to track the motion of stars in the galactic center with remarkable precision. These techniques rely on instruments like the Very Large Telescope, VLT, in Chile and the Event Horizon Telescope, EHT, which have revolutionized our ability to study objects in the extreme environments near black holes. By measuring the star's position over time, scientists can calculate its velocity and determine the shape of its orbit. The data collected so far suggests that this star is moving at speeds that would be impossible to achieve without the immense gravitational influence of Sagittarius A*. Such observations are critical for confirming the existence of black holes and for testing the limits of our physical theories. But why is this star's speed so significant? One reason is that it provides a direct test of Einstein's general relativity. According to Einstein's theory, massive objects like black holes warp spacetime, and this warping affects the motion of nearby objects. The star's extreme velocity offers a unique opportunity to observe how spacetime curvature influences orbital mechanics. If the star's path deviates from what is predicted by general relativity, it could signal new physics at play. However, so far, the star's motion aligns with Einstein's predictions, reinforcing the theory's robustness. This consistency is a testament to the power of general relativity, even in the most extreme conditions. Another aspect of this discovery is its implications for our understanding of stellar evolution. Stars near black holes are often subjected to intense radiation and gravitational forces, which can strip away their outer layers or alter their composition. The star in question may have undergone such extreme conditions, leading to its unique properties. Its high velocity could also mean that it has been influenced by interactions with other stars in the galactic center, where the density of stars is much higher than in other regions of the galaxy. These interactions can transfer energy and momentum between stars, potentially altering their orbits over time. The study of such interactions helps astronomers piece together the complex web of forces that shape the galactic center. The presence of this star also raises questions about the formation and survival of stars in such extreme environments. How did this star form? Did it originate in the galactic center, or was it captured by Sagittarius A* from elsewhere in the galaxy? These are fundamental questions that remain unanswered. Stars near black holes are often part of binary systems, where two stars orbit each other, but this star's motion suggests it may be a single object. Its survival in such a hostile environment is remarkable, as the intense gravitational forces and radiation from the black hole could disrupt or destroy ordinary stars. The fact that this star has persisted for millions of years indicates that it may possess unique characteristics, such as a high mass or a protective shield of gas and dust. Beyond its scientific implications, this star's discovery highlights the importance of long-term observational campaigns in astronomy. The study of stars near Sagittarius A* requires decades of data collection, as their orbits take years to complete. By continuously monitoring these stars, astronomers can detect subtle changes in their motion that may reveal new insights into black hole behavior. For example, the star's velocity could provide clues about the black hole's mass and spin, two properties that are critical for understanding its role in the galaxy. Additionally, the star's trajectory might offer hints about the distribution of dark matter in the galactic center, as dark matter's gravitational influence could subtly affect the star's path. The discovery also underscores the dynamic nature of the galactic center. While Sagittarius A* is often described as a relatively quiet black hole, its surroundings are anything but calm. The galactic center is a region of intense activity, with stars, gas clouds, and other objects interacting in complex ways. The presence of this high-speed star suggests that the galactic center is a place of constant motion and transformation, where the forces of gravity and radiation shape the lives of celestial objects. Studying such phenomena helps astronomers build a more complete picture of how galaxies evolve over time. In conclusion, the discovery of this star orbiting Sagittarius A* at such high speeds is more than just an observation, it's a window into the fundamental forces that govern the universe. By studying its motion, scientists can test the limits of our physical theories, uncover new aspects of stellar evolution, and gain insights into the nature of black holes. This star's journey through the galactic center is a reminder of the vast and complex systems at play in our universe, and it serves as a testament to the power of human curiosity and scientific inquiry. As we continue to explore the cosmos, discoveries like this one will undoubtedly shape our understanding of the universe and its mysteries for years to come. For decades, astronomers have been peering into the heart of our galaxy, where the Milky Way's supermassive black hole, Sagittarius A*, reigns supreme. But it wasn't until the late 20th century that scientists began to notice something extraordinary, a star hurtling through space at speeds that defy intuition. This star, now known as S2, was first observed in the 1990s, but it wasn't until the early 2000s that its true nature became clear. The journey to confirm its existence as a high-speed object orbiting the black hole was a testament to human ingenuity, requiring a blend of cutting-edge technology, patient observation, and a deep understanding of celestial mechanics. Let me take you through how this discovery unfolded, step by step. The first hints of S2's unusual motion came from the European Southern Observatory's ESO, Very Large Telescope, VLT, in Chile. Located in the Atacama Desert, the VLT is one of the most advanced ground-based observatories, equipped with adaptive optics, a technology that compensates for the blurring effects of Earth's atmosphere. By using a deformable mirror that adjusts in real time, the VLT could capture images of the galactic center with unprecedented clarity. These early observations revealed a star moving in an elliptical path around Sagittarius A*, but its speed was unlike anything previously seen. While other stars in the vicinity of the black hole moved at hundreds of kilometers per second, S2's velocity reached thousands, making it a prime candidate for further study. But confirming such a high speed required more than just a single snapshot. The key was to track the star's motion over time, measuring how its position and velocity changed as it orbited the black hole. This meant collecting data over many years, a process that demanded both precision and patience. The VLT, along with other telescopes like the Keck Observatory in Hawaii, became the primary tools for this endeavor. These observatories used spectroscopy, a technique that splits light into its component wavelengths, to determine the star's velocity. By analyzing the Doppler shift of the star's light, scientists could calculate how fast it was moving toward or away from Earth. For example, if the star's light shifted toward the blue end of the spectrum, it meant the star was moving closer. A redshift indicated it was moving away. These measurements, taken repeatedly over decades, allowed researchers to map S2's orbit with remarkable accuracy. One of the biggest challenges was the extreme proximity of the black hole. Sagittarius A* lies about 27,000 light-years from Earth, but its gravitational pull is so intense that even light is affected. This meant that the star's motion had to be measured with extraordinary precision. To achieve this, scientists relied on a combination of ground-based and space-based telescopes. The Hubble Space Telescope, for instance, provided high-resolution images that helped refine the star's position, while radio telescopes like the Very Long Baseline Array (VLBA) offered additional data points. The VLBA, which uses a network of radio dishes spread across the globe, could detect subtle changes in the star's motion by measuring how its radio emissions shifted over time. These observations were critical for confirming that S2's speed wasn't just a one-time anomaly but a consistent feature of its orbit. Another breakthrough came with the development of more advanced adaptive optics systems. Early versions of this technology allowed astronomers to reduce atmospheric distortion, but newer systems, like those at the VLT and the upcoming Extremely Large Telescope (ELT), could achieve even greater resolution. The ELT, currently under construction, will have a mirror over 39 meters in diameter, large enough to capture light from objects in the galactic center with incredible detail. While the ELT hasn't been used for this particular study, its potential underscores how far the field has advanced. For S2's discovery, however, the VLT's adaptive optics were sufficient to reveal the star's motion with enough precision to rule out alternative explanations. The timeline of observations was equally important. S2's orbit around Sagittarius A* takes about 16 years to complete, meaning scientists had to wait nearly 2 decades to see the full cycle of its motion. This long timescale made the study of S2 a marathon rather than a sprint. Each observation required meticulous planning, as the star's position in the sky changed over time, necessitating adjustments to telescope pointing and data collection methods. The patience required for this work was immense, as even a single misstep could lead to errors in the final calculations. Yet, the payoff was profound. By the early 2010s, astronomers had gathered enough data to confirm that S2's speed was indeed extraordinary, reaching up to 22,000 kilometers per second, over 7% of the speed of light. For context, this is faster than any other star known to orbit a black hole, making S2 a unique subject of study. But how did scientists ensure that these measurements were accurate? One of the key methods involved comparing the star's motion to the predictions of Einstein's theory of general relativity. According to Einstein's equations, a massive object like Sagittarius A* should warp spacetime in such a way that a star orbiting it would experience relativistic effects. These effects include time dilation, where time appears to slow down near a massive object, and gravitational redshift, where light from the star is stretched to longer wavelengths. By measuring these effects, scientists could test whether their observations aligned with the predictions of general relativity. For example, if S2's light showed a redshift consistent with its high velocity, it would support the idea that the star was indeed moving at such an extreme speed. These tests not only confirmed the star's motion but also provided a real-world validation of one of the most important theories in physics. The confirmation process also involved ruling out alternative explanations. Could S2's high speed be due to some other phenomenon, like a gravitational anomaly or a nearby star's influence? To address this, scientists cross-referenced their data with observations from other telescopes and simulations of the galactic center. They also considered the possibility of measurement errors, which could arise from instrumental limitations or atmospheric interference. By combining data from multiple sources and using statistical methods to analyze the results, researchers could confidently attribute S2's motion to its orbit around Sagittarius A star. This rigorous approach ensured that the findings were not just observational but also theoretically sound. Perhaps the most impressive aspect of this discovery is the scale of collaboration it required. Studying S2 involved a global network of astronomers, engineers, and physicists working together to share data, refine techniques, and overcome technical challenges. The VLT, for example, was a joint effort between multiple countries, and its success relied on the expertise of teams across Europe. Similarly, the use of space-based telescopes like Hubble and the VLBA highlighted the importance of international cooperation in astronomy. These collaborations were essential not only for gathering data but also for interpreting it, as the complexity of the galactic center demanded a multidisciplinary approach. In the end, the confirmation of S2's high-speed orbit around Sagittarius A** was a milestone in astrophysics. It demonstrated the power of modern observational techniques and the importance of long-term studies in understanding cosmic phenomena. The journey to uncover this secret was not just about measuring a star's speed, it was about pushing the boundaries of human knowledge, using tools that once seemed impossible and patience that spanned decades. Today, S2 remains a focal point for research, offering insights into the behavior of black holes, the nature of gravity, and the extreme environments that exist at the heart of our galaxy. Its story is a reminder that the universe is full of mysteries waiting to be uncovered, and that with the right tools and determination, even the most elusive secrets can be revealed. In the heart of our galaxy, where the Milky Way's gravity is strongest, a star is hurtling through space at mind-bending speeds, so fast, in fact, that it's orbiting a supermassive black hole at the galaxy's center. This isn't just a spectacle of cosmic motion, it's a window into the fundamental forces that shape the universe. To understand why this star's journey is so significant, we have to look at the interplay between gravity, motion, and the extreme environments around black holes. These observations aren't just about tracking a single star, they're about unraveling the mysteries of how galaxies form, how black holes influence their surroundings, and how the laws of physics hold up in the most extreme conditions imaginable. At the core of our galaxy lies Sagittarius A**, a black hole with a mass equivalent to millions of suns. Its gravitational pull is so intense that it warps spacetime around it, creating a region where the rules of classical physics begin to bend. Now, imagine a star, a massive, luminous object, moving through this gravitational landscape. The star's orbit isn't just a simple circle, it's a dance of forces, where the black hole's gravity acts like an invisible tether, pulling the star into a tight, fast-paced loop. The star's speed is so high that it's moving at a fraction of the speed of light, yet it remains in a stable orbit rather than being torn apart by the black hole's gravity. This balance between motion and gravity is a testament to the precision of the laws that govern the cosmos. But why is this particular star's motion so noteworthy? For one, it's part of a rare class of objects known as S-stars, which orbit the galactic center at velocities that challenge our understanding of how such systems form. These stars are not just randomly distributed, they're arranged in a way that suggests they've been influenced by the black hole's gravity over millions of years. By studying their orbits, astronomers can map the black hole's mass and test the predictions of Einstein's theory of general relativity. In fact, the way these stars move provides some of the strongest evidence yet that Sagittarius A* is indeed a supermassive black hole, rather than some other exotic object. The precision of their orbits, combined with their high speeds, allows scientists to measure the black hole's mass with remarkable accuracy, confirming that it's roughly 4 million times the mass of our Sun. Yet, the significance of this star's journey goes beyond just the black hole itself. The fact that it's moving so fast means it's also interacting with the surrounding environment in ways that reveal hidden aspects of the galactic center. For example, the star's motion could be influenced by the presence of other stars, gas clouds, or even dark matter in the region. These interactions create a dynamic, ever-changing landscape around the black hole, and studying them helps astronomers piece together the complex web of forces at play. Moreover, the star's high velocity means it's likely to pass close to the black hole in the future, a scenario that could provide a unique opportunity to observe how extreme gravity affects matter in real time. Such events are rare, but they offer a chance to test the limits of our physical theories and glimpse the nature of spacetime under extreme conditions. The physics behind this star's motion is rooted in the fundamental principles of gravity and orbital mechanics. According to Newton's law of universal gravitation, the force between two objects depends on their masses and the distance between them. In this case, the star's orbit is determined by the balance between its own inertia, the tendency to move in a straight line, and the gravitational pull of Sagittarius A star. The closer the star is to the black hole, the stronger the gravitational force, which means the star must move faster to maintain its orbit. This is why stars near the galactic center orbit at such incredible speeds. They're caught in a gravitational tug-of-war with the black hole's immense mass. However, Einstein's theory of general relativity adds another layer to this story. It predicts that massive objects like black holes not only warp spacetime but also cause time to dilate, meaning that time would run slower near the black hole compared to regions farther away. While we can't directly measure this effect on the star itself, the star's motion provides indirect evidence that general relativity holds true in these extreme environments. What makes this star's orbit particularly interesting is its potential to shed light on the nature of dark matter. Dark matter is a mysterious substance that doesn't interact with light but exerts gravitational effects on visible matter. While the galactic center's gravitational field is dominated by Sagittarius A*, the presence of dark matter could subtly influence the motions of nearby stars. By analyzing the star's trajectory and comparing it to predictions based on visible matter alone, astronomers can search for signs of dark matter's gravitational pull. If the star's motion deviates from what's expected, it could hint at the presence of dark matter in the region. This isn't just a theoretical exercise, it's a way to probe one of the greatest mysteries in modern astrophysics: what exactly makes up the vast majority of the universe's mass? Beyond the immediate implications for black holes and dark matter, this star's journey also offers insights into the life cycles of stars in extreme environments. The galactic center is a region of intense activity, with high-energy radiation, magnetic fields, and violent stellar interactions. Stars that orbit close to a black hole are subject to these extreme conditions, which can strip away their outer layers, accelerate particles to near-light speeds, or even trigger bursts of radiation. The fact that this star has survived for millions of years despite these challenges suggests that it's either exceptionally resilient or that the black hole's environment is more stable than previously thought. Studying such stars helps astronomers understand how stars evolve in the most extreme gravitational fields, providing clues about the lifetimes, fates, and behaviors of stars in different parts of the galaxy. Moreover, the observation of this star's motion has practical implications for our understanding of the Milky Way's structure and evolution. The galactic center is a key region for studying how galaxies form and change over time, and the presence of a supermassive black hole at the center is a defining feature of most large galaxies. By tracking how stars like this one move around the black hole, astronomers can build detailed models of the galaxy's gravitational field. These models, in turn, help us understand how the Milky Way has grown over billions of years, how its spiral arms form, and how the black hole's gravity influences the motion of stars across the entire galaxy. In essence, this star's orbit is a tiny piece of a much larger puzzle, one that connects the fate of individual stars to the grand architecture of the universe. The significance of this star's motion also extends to the broader field of astrophysics, where such observations are used to test the limits of our physical theories. For example, the way this star moves around the black hole could provide a unique opportunity to study the effects of general relativity in a regime where spacetime is highly curved. While we've tested Einstein's theory in many contexts, such as the bending of light around the sun or the time dilation experienced by GPS satellites, observing stars in the immediate vicinity of a supermassive black hole offers a new frontier. These observations can help confirm whether general relativity holds true in extreme conditions or whether new physics might be required to explain what's happening in such a gravity well. Such tests are crucial for advancing our understanding of the fundamental laws that govern the universe. In addition to its scientific value, this star's journey also serves as a reminder of the vast scales and forces at play in the cosmos. The fact that a single star can orbit a black hole at such incredible speeds is a humbling reminder of how much we still have to learn about the universe. It's a testament to the power of gravity, the precision of physical laws, and the ingenuity of astronomers who use these observations to probe the unknown. Every time we study such a system, we're not just looking at a star moving through space, we're peering into the very fabric of reality, seeking answers to questions that have puzzled scientists for centuries. Ultimately, the story of this high-speed star is more than just a tale of motion and gravity. It's a story of discovery, of how the universe operates on scales we can barely comprehend, and of how the tools of science allow us to glimpse the extraordinary. By studying this star's orbit, we're not only learning about the black hole at the galaxy center, we're uncovering the fundamental principles that shape the cosmos. And in doing so, we're taking one more step toward understanding our place in the universe, and the forces that govern it. For decades, astronomers have gazed toward the heart of our galaxy, the Milky Way, where a supermassive black hole lies hidden in the dense, chaotic light of the galactic center. But the journey to understand this region, its mysteries, its extremes, and the strange objects that orbit its event horizon, has been a slow, methodical unraveling of the cosmos. It began not with the discovery of the black hole itself, but with the realization that something massive and unseen must be at the core of our galaxy. This revelation, pieced together over decades, laid the foundation for the modern understanding of stars hurtling through space at incredible speeds, their orbits dictated by the gravitational pull of a black hole millions of times more massive than our Sun. To grasp how we arrived at this moment, we must travel back through time, to the early days of radio astronomy, the development of ground-based telescopes, and the breakthroughs that transformed our view of the universe's most extreme environments. The story starts in the 1970s, when radio telescopes first began to peer into the galactic center. At the time, the region was shrouded in confusion. The center of the Milky Way, located in the constellation Sagittarius, was a place of intense stellar density, obscured by interstellar dust and gas. Yet, radio waves, which can penetrate these veils, revealed a strange signal, a bright radio source named Sagittarius A*, SGR-A*. This was no ordinary star. Its brightness suggested something massive, but its lack of visible light hinted at something even more extraordinary, a black hole. However, the evidence was indirect. The radio glow could have been caused by a dense cluster of stars or a massive object, and without direct observation, the nature of SGR-A* remained uncertain. Scientists were left with a tantalizing mystery: what exactly was at the heart of our galaxy? The next major leap came in the 1980s, when astronomers began to notice something remarkable about the stars near SGR-A star. Using ground-based telescopes, they observed a group of stars moving in tight, elongated orbits around the galactic center. These stars, including one later named S2, were moving at speeds that defied conventional understanding. For instance, S2's orbit around the black hole is so elliptical that it comes within just a few astronomical units, about 10 times the distance between Earth and the Sun, of the event horizon. Such extreme velocities suggested that the unseen object at the center must be incredibly massive. But even then, the evidence was incomplete. The star's motions were too slow to confirm the presence of a black hole with certainty. The challenge was that the galactic center's dense interstellar medium made it difficult to observe these stars in visible light, and the precision required to measure their orbits was beyond the capabilities of existing telescopes. The 1990s marked a turning point. The development of adaptive optics, a technology that allows telescopes to compensate for atmospheric distortion, enabled astronomers to capture sharper images of the galactic center. This breakthrough, combined with the use of infrared telescopes, allowed scientists to peer through the dust and gas that had long obscured the region. Infrared light, which is less affected by interstellar material, became the key to unlocking the secrets of the galactic core. With these tools, astronomers could now track the motion of individual stars, including S2, with greater accuracy. The results were staggering. S2's orbit, first measured in the 1990s, confirmed that the object at the center of the galaxy must be a supermassive black hole. The star's extreme speed, reaching up to 2.7% the speed of light, provided the first concrete evidence that something with immense gravitational pull was governing the motion of these stars. Yet, even with these observations, the black hole itself remained invisible. Its presence was inferred through the motion of the stars, much like how we infer the existence of planets by observing the wobble of their host stars. The 2000s brought another wave of progress, driven by the development of advanced instruments and the launch of space-based observatories. The Keck Observatory in Hawaii, equipped with adaptive optics, became a critical tool for studying the galactic center. Meanwhile, the European Southern Observatory, ESO, launched the Very Large Telescope, VLT, which allowed for even more precise measurements of stellar orbits. These efforts led to the discovery of additional stars in the galactic center, including S3, S4, and others, each providing further evidence of the black hole's gravitational influence. One of the most significant milestones came in 2002, when a team of astronomers, including Reinhard Genzel and Andrea Ghez, published a study that confirmed the existence of a supermassive black hole at the galactic center. Their work, which relied on decades of observations of S2 and other stars, demonstrated that the black hole's mass was approximately 4 million times that of the Sun, a figure that would later be refined through more precise measurements. The 2010s ushered in a new era of precision, thanks to the advent of instruments like the gravity interferometer, which combined the power of multiple telescopes to achieve unprecedented resolution. This technology, developed by the ESO, allowed astronomers to measure the orbits of stars like S2 with extraordinary accuracy. The Gravity team's 2018 study, which tracked S2's motion over multiple orbits, provided the most detailed data yet on the black hole's gravitational effects. These observations not only confirmed the existence of the black hole but also revealed subtle details about its properties, such as its mass and spin. The data also hinted at the presence of an accretion disk, a swirling disk of gas and dust that orbits the black hole and emits intense radiation. These findings were a major step forward, bridging the gap between theoretical models of supermassive black holes and the real-world observations of their effects on surrounding stars. In parallel, the Gaia mission, launched by the European Space Agency (ESA) in 2013, revolutionized our understanding of the Milky Way's structure and dynamics. Gaia's ability to map the positions, distances, and velocities of billions of stars provided a new perspective on the galactic center. While Gaia's primary focus was not the galactic center, its data helped refine models of the galaxy's gravitational field, offering insights into how the black hole's presence influences the motion of stars across the entire galaxy. Additionally, the Event Horizon Telescope (EHT) project, which culminated in the first-ever image of a black hole in 2019, provided a visual confirmation of the existence of Sagittarius A star. The EHT's image, which captured the shadow of the black hole against the glowing accretion disk, was a milestone that validated decades of theoretical predictions and observational data. This achievement not only solidified the black hole's existence but also opened new avenues for studying its interactions with surrounding matter. As we approach the present day, the study of stars like S2 continues to evolve, driven by increasingly sophisticated technology and a deeper understanding of the physics governing the galactic center. The latest observations, which have refined the measurements of S2's orbit and the black hole's properties, have allowed scientists to test Einstein's theory of general relativity in extreme conditions. For example, the 2020 study by the Gravity team, which combined data from multiple decades of observations, confirmed that the black hole's gravitational field behaves exactly as predicted by general relativity. These findings are not just academic, they have profound implications for our understanding of gravity, spacetime, and the fundamental laws that govern the universe. By studying stars like S2, astronomers are not only mapping the galactic center but also probing the limits of our physical theories, seeking to uncover the secrets of the cosmos in ways that were once unimaginable. The journey to understand the high-speed star orbiting Sagittarius A* is a testament to the power of human curiosity and technological ingenuity. From the early days of radio astronomy to the precision of modern interferometers, each step forward has brought us closer to revealing the hidden truths of the universe. The stars that orbit the black hole are more than just celestial objects, they are living laboratories, offering insights into the nature of gravity, the structure of spacetime, and the extreme environments that exist at the heart of galaxies. As we continue to refine our observations and push the boundaries of what is possible, the story of the galactic center will undoubtedly unfold in new and exciting ways, revealing the profound connections between the smallest particles and the largest structures in the cosmos. This star, hurtling through space at unimaginable speeds, has become a focal point for astronomers seeking to unravel the secrets of the supermassive black hole at the heart of our galaxy. Yet, despite the wealth of data gathered over the years, several profound questions remain unanswered. How exactly does this star maintain such an extreme orbit? What does its motion reveal about the black hole's nature that we still don't fully grasp? And could this system hold clues to phenomena beyond our current understanding of physics? These mysteries are not just academic, they are central to our evolving picture of how galaxies, black holes, and stars interact on the grandest scales. Let's dive into the unresolved enigmas that continue to captivate scientists and stoke the fires of discovery. One of the most pressing questions revolves around the star's orbit itself. While we have mapped its path with remarkable precision, certain aspects remain elusive. For instance, the exact shape of its trajectory, whether it's perfectly elliptical or subtly perturbed by unseen forces, still sparks debate. Some researchers argue that the star's motion suggests the presence of additional mass in the galactic center, perhaps in the form of dark matter or a hidden companion object. Others propose that gravitational interactions with nearby stars or gas clouds could be nudging the star's path in ways we haven't yet modeled. These possibilities are not mere speculation, they're rooted in the limitations of our current observational tools. The farther we peer into the galactic center, the more we realize how much remains hidden behind the veil of interstellar dust and the intense gravitational lensing caused by Sagittarius A* itself. Another layer of mystery lies in the black hole's own properties. While we know its mass to be roughly 4 million times that of the Sun, the precise details of its spin and charge remain uncertain. The star's high-speed orbit could, in theory, provide critical insights into these characteristics. For example, if the black hole is spinning rapidly, its gravity would exert a different kind of pull on the star compared to a non-rotating black hole. Yet, the data we've collected so far doesn't conclusively resolve this question. Some models suggest that the star's motion aligns with a black hole spinning in a particular direction, while others argue that the observed patterns could be explained by a combination of factors, including the star's own peculiar velocity or the gravitational tugs of nearby stellar remnants. These uncertainties highlight how much we still have to learn about the fundamental nature of black holes, even in our own galaxy. The star's environment also presents a puzzle. The galactic center is a chaotic region, teeming with stars, gas, and magnetic fields that could influence the star's behavior in ways we're only beginning to understand. For instance, the star's proximity to Sagittarius A* means it's constantly subjected to intense tidal forces, gravitational pulls that could stretch it or even tear it apart under the right conditions. Yet, the star has survived for millions of years, suggesting that either the black hole's gravity is less extreme than we think, or the star has some protective mechanism, like a dense shell of gas or a unique orbital configuration. These possibilities are not just theoretical, they're part of an active scientific discussion about how stars can endure in such hostile environments. Some researchers even wonder if the star's survival could be a sign of deeper, unexplored physics at play. Beyond the immediate system, the star's existence challenges our understanding of how stars form and evolve in extreme gravitational fields. Most stars in the galactic center are thought to have formed there, but this star's orbit suggests it might have been captured from elsewhere in the galaxy. If that's the case, how did it end up in such a close orbit? Some theories propose that it was pulled in by the black hole's gravity during a close encounter with another star or a dense cluster of stars. Others suggest that it formed in a different region and was flung into its current path by a supernova explosion or a gravitational wave event. These scenarios are not mutually exclusive, but they all require further investigation. The star's unique trajectory could provide a Rosetta Stone for understanding the dynamics of star formation in the presence of supermassive black holes, a topic that remains hotly debated in astrophysical circles. Moreover, the star's behavior may offer clues about the nature of spacetime itself. General relativity has been remarkably successful in predicting the behavior of objects near black holes, but there are still gaps in our understanding. For example, the star's motion could be influenced by effects that go beyond Einstein's equations, such as quantum gravity phenomena or the presence of exotic matter in the black hole's vicinity. While these ideas are speculative, they are not entirely out of reach. The extreme conditions near Sagittarius A* could, in theory, create a laboratory for testing the limits of our physical theories. Yet, the data we've gathered so far doesn't provide definitive evidence for or against these hypotheses, leaving the door open for future discoveries. The challenges of observation also play a role in the unresolved questions. The galactic center is one of the most difficult regions in the universe to study, obscured by thick clouds of interstellar dust and the intense radiation from the black hole's accretion disk. Even with the most advanced telescopes, we can only glimpse this region indirectly, relying on the light emitted by nearby stars and the subtle distortions caused by gravitational lensing. These observational constraints mean that some aspects of the star's motion and the black hole's influence remain shrouded in uncertainty. For instance, we can measure the star's position and velocity with high precision, but we can't directly observe the black hole itself. This reliance on indirect methods introduces margins of error that scientists must constantly work to minimize, yet they also fuel the creativity needed to interpret the data in new ways. Finally, the star's existence raises questions about the broader implications for our understanding of galaxy evolution. Supermassive black holes are believed to be central to the formation and structure of galaxies, but the exact mechanisms remain unclear. This star's orbit could be a microcosm of larger-scale processes, such as how black holes regulate star formation in their host galaxies or how they interact with the surrounding interstellar medium. If the star's motion is influenced by factors beyond the black hole's gravity, such as magnetic fields, dark matter, or the collective motion of nearby stars, then it could provide a unique window into these complex interactions. However, without more data, these connections remain speculative, and the scientific community continues to grapple with how to reconcile the star's behavior with existing models of galaxy dynamics. In the end, this star's story is a testament to the enduring allure of the unknown. It is a beacon of curiosity, drawing astronomers into a dance of observation, hypothesis, and imagination. While we have made tremendous strides in understanding the galactic center, the questions it raises are as vast as the cosmos itself. Each unresolved mystery is not a dead end but a stepping stone, guiding us toward new discoveries and deeper insights. As technology advances and new telescopes come online, the next chapter of this story may yet unfold, revealing secrets that have eluded us for decades. Until then, the star's high-speed journey around Sagittarius A** remains a reminder of how much there is still to learn about the universe we call home. This high-speed star is whipping around the black hole in the middle of our galaxy. This part of our deep dive into this high-speed star is whipping around the black hole in the middle of our galaxy focuses on, explain what's coming next, future missions, instruments, or observations that could confirm, extend, or challenge what we know so far. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. Imagine a star hurtling through space at speeds that defy imagination, so fast, in fact, it's racing around a black hole at the very heart of our galaxy. This isn't just any star, it's a cosmic outlier, orbiting the supermassive black hole Sagittarius A* in a path so tight and swift that it completes a full loop in just a few years. Scientists have been tracking this star for years, and what they've discovered is rewriting our understanding of how stars interact with black holes. First, this star's velocity is a direct clue to the black hole's immense gravitational pull. By measuring how fast the star moves, astronomers can calculate the black hole's mass with extraordinary precision. It's like watching a tiny planet orbit a giant sun, but here, the sun is a black hole 4 million times the mass of our own. Second, this star isn't alone. It's part of a rare binary system, locked in a dance with another star. This dual relationship creates a unique lab for studying how black holes influence their surroundings. The gravitational tug-of-war between the two stars and the black hole reveals secrets about the dynamics of these extreme environments. Third, this star's existence challenges our assumptions about star formation near black holes. How did it form? How does it survive in such a hostile neighborhood? These questions are driving new research into the life cycles of stars in the galactic core. What makes this star so special isn't just its speed, but the window it provides into the invisible forces shaping our galaxy. Every observation adds another piece to the puzzle of how black holes sculpt the cosmos. As we unravel these mysteries, we're reminded that the universe is a place of both chaos and order, where the dance of gravity and light continues to surprise us. If you've enjoyed this deep dive, hit subscribe for more explorations of the cosmos. And if you have your own theories or questions about this star's journey, drop them in the comments. We're always curious to hear what you think.